Okay, Assalamualaikum and good afternoon. So we continue
Yes,
our lecture. So before we go for the tutorial for chapter 2, I would like to show here the simple example for the Buckingham Pi theorem because might be one of you or a few, maybe it's just to refresh your memory about the Buckingham Pi theorem. Okay, so because last just now, so there are students say that so he didn't know about the Buckingham Pi theorem, so we go for this one, and I hope you could do the self study for the Buckingham Pi theorem. So for example, we have a situation like this. This is example 3. So water sloshed back and forth in the tank as shown in figure 1. So you could imagine that if you move this tank, so the water level will go up and down. So the frequency of sloshing is assumed to be a function of the acceleration of gravity, the average depth of water h, and the length of the L. So the question is develop a suitable set of dimensionless parameter for this problem using G and L as repeating variable. So we start to answer this by looking the idea of frequency of sloshing is assumed to be a function of the acceleration. So the words a function of the acceleration will turn your, you start your calculation by this one. So by change the word, the frequency is assumed to be a function of blah 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 into this term of this mathematical term. So we have omega is a function of gravity, height, and L length. So and then what you do is you play around with the units. So for example, omega is the frequency. So the unit is only 1 over s. So we write it as t time minus 1. And gravity is length time minus 2. And h is length. And L is also length. And from the question, they ask us to use G and L as repeating variable. So repeating variable here is actually present the 3 parameter that we discussed previously. So one is the about length. So number 2 is actually about the velocity, the kinematic. So we have meter per second, now we have meter, and the third one is actually about the dynamic. So anything that relate to the meter per second mass, kilogram here. Okay, however, for this situation, we don't have any terms about kilogram. So it is okay for us just to take this value and also this value. Means that our parameter is now reduced from 3 to 2 parameter. So and then we need to develop, that's why we call this process is Buckingham Pi theorem, because we need to develop our pi here. So how to determine the value of pi? So because we only have 2 repeating parameter here, and then the total parameter is 4. Now 4 minus 2, so means that we only have, we need to construct another 2 parameters. So this 2 is actually 2 pi parameter. So the idea is, okay, we write down like this one. So pi 1 is equal to omega. Okay, and then because from the question, we take a G and L as the repeating variable. So why it's called repeating variable? Because the value of G and L will be appear in both terms, in pi 1 and also in pi 2. So both parameter will be appear because it will it's repeat itself. So we call this G and L as a repeating variable. So we give G by the power of A and L is the power of B. So this is the rule. And we multiply with the omega, which is not the repeating parameter. And then for pi 2, we multiply with H with another non-repeating parameter. So omega and H cannot be used more than 1 because it is not a repeating parameter. So and then what we do is, Okay, for example, for pi 1, okay, we just assume that dimensionless parameter means there are no units. So no units means the value of mass, length, and times will have power of 0. So we have m0, l0, and t0. And then we substitute this one. So for example, omega here is the frequency. So the unit is 1/second. But in Buckingham pi theorem, we don't use 1/s. We don't use s for the second. So we use t for the time. Okay, so we substitute here. So omega is t minus 1. So g is l t minus 2 by the power of a. Okay, please don't forget about this. And l is the length by the power of b. And I think you know to solve this one. So because the value here is the same, so we could say that 0 is equal to a plus b, and 0 is also equal to minus 1 minus 2a. So if we do the calculation here, we could get that the a here is minus 1/2 and l is equal to 1/2. So then we could write pi 1 is equal to omega square root l over g. So, and then for pi 2, we do the same things. So we have pi 2 h g by the power of c and l by the power of d. And then we do the same thing here. And finally, we will get pi 2 is equal h over l. And finally, we write down the final answer for this situation is omega square root l over g is equal f h over l. These two parameters actually, this two parameter is the dimensionless parameter, because if you see h over l, they will leave us no unit, and also omega l over g square root here will give us no units. So these actually two dimensionless parameter that can be used for question number 3 situation, for this situation. So mean if we have this situation, okay, you are not allowed just to pick up Reynolds number and use in this situation. No, you cannot actually do the dimensionless parameter and then you will get your own dimensionless parameter. Because sometimes if you neglect certain parameter, for example, in this case, might be you neglect the density of the fluid, then your dimensionless parameter will not have terms of density. Okay, this is the very simple example for Buckingham pi theorem. So we go back to our chapter 2 tutorial here. Okay.
Thank you very much, sir.
So I think you could make a revision for this one. Okay.
Inshallah. Yes, sir.
Okay.
Yes, sir. Yes, sir. Very good. Thank you.
Okay. So this I take selected question from the textbooks to discuss, and some of them is already discussed in our lecture. Okay, so for example, for this one, I think I could skip it, or I just go a little bit faster. So we need to derive the continuity equation for the cylindrical coordinates. So we have this cube, and you already know, so this is the radial axis, so this is the theta axis. So, and then this is the z-axis, the thickness of that molecules. So, for continuity equations, so we use this equation, mass flow rate at inlet minus mass flow rate at outlet, and it must be equal to changes of mass over time inside that molecules. So, I think you have these notes. So we do all this calculation here. So finally, okay, first we do for the R axis, then we calculate for the Z axis, and then we have the theta axis here. Okay, and then we calculate the mass, which is equal to rho volume. I think you know how to convert this. Normally, it starts with the density is equal to mass over volume, then mass is equal to rho times volume. And then if you do all of this, okay, and then again, I would like to remind you here, you also needs to understand all the terms here and try to relate with your own work. For example, the value of drdt here, it exists in the calculation, but in real situation, the physical meaning of the physical meaning of dr over dt means the changes of radius over time, because we assume that the radius is constant uh, at all time. So we could say that dr over dt is equal to 0. So and then if you solve everything, you could get this is the continuity equation for the polar coordinate. So another okay, so this is for polar coordinates or cylindrical coordinates. Okay, I'm sorry. So in my previous notes, I'll show you how to simplify this one if it is only two-dimensional and it used for incompressible flow. So you could neglect the value of rho and so on and so forth. So so 2.2, for example, simplify the equation of continuity in cylindrical coordinates. We have r, theta, and z to the case of a steady compressible flow. In polar coordinates, del z equal to 0. So and then derive a stream function for this case. Okay. Okay. So steady compressible flow means that as we know that, okay, so we have a for it. Okay, we have a cylinder here. Okay, and then if you have a okay, this is the center line. Okay, so and then the molecule will move parallel with the radials, and then it also tangent to the circular shape. So which is, this is the UR and this is the U theta, because it will reflect the theta here. And then the molecule will also move at this direction, which is Z. So and then the steady compressible flow here is how we determine the steady flow. I hope you could make a revision about the steady and unsteady, uniform and non-uniform. So the basic concept is steady is actually the condition of molecule which is not changed along the time. So means that if you check this molecule, okay, might be it is T1, and then after a certain time it move until this location. So for example, T equal 5 seconds, for example. If you check this molecule, okay, or you check this time frame, you will find that there are no changes. Okay, if there are no changes along the time, so means the velocity is steady. Okay, so for this one, so because this is the common way we evaluate the molecule flow on pipe in this situation, that's why we call it dz. The ddz is equal to 0, because there are no changes along the axis of z. But maybe this molecule has different velocity here and so on and so forth, because the component of UR and U theta is exists. Okay, this is the idea of this question. Okay, so okay, let me. Okay. Okay, and then because they asked about the continuity equation, so you comes out with the continuity equation. So we have term of VR, we have term of Vz, and then we have terms of V theta. And because the steady flow, so we assume that it is dz is equal to 0, and also the dt is equal to 0. Okay. So and then we could simplify our continuity equation as this one. So and then we could solve this problem because we know the equation for velocity here. So it from the Cauchy-Riemann equation. So we learn how to develop this equation first. So the VR is d psi over r d theta, and v theta is equal to d negative d psi over dr. And we know that psi here is actually reflect the mass flow rate. So it can be calculated by using the idea of rho AV, or V is equal to psi over rho A. Okay, so and then so we have okay, so and then we have a VR here. It can be written by using this idea and also this idea as 1 over rho psi del psi over r del theta, and equal this one, and v theta is also negative 1 over rho del psi over del r. Okay, so we have this one. So how to get the stream function is actually, so might be I left the solution. So the idea is we could bring all of these and then we could integrate for both side. So as you know, so we have a d psi here, and then we have rho r del theta, and we could bring to the left side. Okay, and then you could integrate for both situation. And then because we have a two velocity here, so what you need to do is you need to compare this your answer for VR and your answer for V theta, and then you could merge the calculation. Okay, so please try to do this. Okay, might be I left my my answer for this one. Okay, and then for 2.3, for example.
Excuse me, Professor.
Yes.
In the last page, what was? Can you tell us what was written within the bracket?
What was written in the bracket here?
Yes. Yes.
In
The
bracket.
last line. Yes. After V theta. Is it in Malay?
Oh, in the bracket. See, this the counterclockwise. So this means counterclockwise because we have the negative sign here.
Okay, Professor. Thank
Okay,
you.
so okay then. So this is actually I hope in your undergraduate you have this question, because in UTM for our undergraduate we solve this one actually. Okay, but as I said, the idea is you just bring everything is here, and then you integrate both side, you will get the value of psi. But that value is actually your psi at r axis. And then again here, if you do the same thing, you will find that you could get your psi here, but the psi is actually for the theta axis. And you know that psi is flow rate. Mean flow rate is, if you want to merge the flow rate, so you need to just sum them up. So what you need to do is you just sum these two parameters, and you will get the total stream function. Okay, for 2.3, simplify the equation of continuity in cylindrical coordinates to the case of steady compressible flow in asymmetric coordinates. So which is the theta del over del theta is equal to 0, and derive a stream function for this case. So again, so this is just the practice. So we assume that del theta is equal to 0. So we have the continuity equation here. So we assume that del theta is equal to 0 means that there are no changes in theta direction. So v theta is also equal to 0. So because it is steady flow, so there are no changes of time. So and then we could simplify our continuity equation is like this. So we have this one, and again, you need to understand that R is constant. Okay, wait a minute. Okay, I'm sorry. We have okay. So for the sake of recording, so I start here. So this is question for 2.3. So simplify the equation for continuity in cylindrical coordinates to the case of a steady compressible flow in asymmetric coordinates. So we assume that del d theta is equal to 0 and derive a stream function for this case. So this the common continuity equation that we derived previously. So we assume that del over del theta is equal to 0, and the value of v theta is also equal to 0, and because it is a steady flow, so we assume there are no changes along the time, so we have a del dt over to 0. Del over dt is equal to 0. So this is the after we substitute all the value, so this is our continuity equation. And again, so I hope you could understand that the value of r must be constant. So and then we could develop the relation between the psi here by having this one. So we have a rho vrr equal d psi dz, and vr is equal to 1 over so VR is equal 1 over rho R, and this side is equal del Z, and so and then for the other term is like this. Okay, wait a minute, another one. Okay, I'm sorry again. Okay, so this is for question 2.11. So we have a differential equation for irrotational plane compressible.
Excuse me, Prof.
Yes,
Please, for the question 2.2 and 2.3,
yes,
we were asked to calculate the stream functions, right?
yes.
Can we have the final answer so that when we finish our integration, we can know if our answer is correct or not?
Okay, it's okay. I will
All right,
show
thank
you
you.
the final answer. Okay.
All right, thank you.
Okay, thank you. Okay, so this is the question 2.11. So we have the differential equation for irrotational plane compressible gas flow. So you have this one. So and then the phi is the potential velocity potential, and A is the variable speed of sound in the gas. In the spirit of section 2.9.2, non-dimensionalize this equation and define any parameters which appear. So we give the non-dimensional variable as shown here. So we have phi star, we have velocity and A star here, X and Y star and T star here. And as I previous, you could substitute all these in this one, and then you could divide with the common one. So and then you will have these final terms. So then we found that there are no dimensionless parameter appear. But however, if we see clearly, so we have an A star here. So in some calculation, if the A here can be turned into a speed of sound, but we are not, because when our discussion is going in Mach number, so it will include, it will we need to bring the idea of compressible flow. So usually in this course, so we are limit our situation in the speed is not increase until the 0.3 Mach number. Okay, so means that we try to neglect the idea of compressible. So this is again 2.13. So the equation of motion for free convection near a hot vertical plate for incompressible flow with constant property. So here might be you have something you think that you cannot imagine this kind of situation, but it is okay for dimensionless parameters problem. For example, as I show you in the first lecture, in example 3, when we have a sloshing, a water sloshing and so on, it is okay for us not to know the real situation, because we are only evaluating the units or the dimension of that equation. So for example, we have all of this. Okay, so we have the continuity equation here, and then we have equation that have a temperature and so on and so forth, and we have all the dimensionless variable here. So the same idea is we need to substitute the value of all of these into this equation, because we have a 3 equation, so we need to do it 3 times. Okay, so for example, for equation 1, so this is the continuity. So we substitute all the value, and finally there are no value appear in this final term. So we say that there is no dimensionless parameter can be used. So this is for equation 2. So we have all of this. You substitute with all of that, and I already teach you how to solve with the del square u over del x square and so on and so forth here. Yeah, you could refer the notes, and you need to substitute in this equation. So I just divide into left hand side and right hand side here. So you have notes here, and finally you will get the del square u del x square and del square u del y square as this one. So and then you could substitute, so you could get this one. Okay. And then if you equalize the left hand side and the right hand side, so you divide with v square over l square l cube here, so you will find that we will have this term l square over v nu square g beta and so on. So we will find that this is actually we call as a Grashof numbers. Okay, so that's why I think after this you will do your master projects, and you will download a lot of journal if you do your master project about in fluid mechanics, or you try to do simulation in fluid mechanics and so on. That's why you could see that people will do certain graph plotting by using the dimensionless number. Grashof number is one of the famous number using with the temperature. So this is for the equation 3. So we have these terms, and this is the dimensionless parameter. So I give you the table here. So we substitute everything. So I think you know, you could snapshot this tutorial. So you substitute everything, and this is the nodes to get the value of del square t over del x square. And finally, we will get this one. And then we could get we could compare the value for x and y here. So the del square t over del y square is equal to this one. So and then if we substitute all the values, we could get this one. So this is for the left hand side. So this is for the right hand side. So if we equalize the left hand side and right hand side here, and you know what to do, we try to take out, we try to write in its previous equation, means the first equation that comes out in the question. So and then you will find that there is a difference in this term k over rho CPV. So and then this is actually, we call it as a Prandtl number.